Okay, so I will get started. Thanks everyone for joining this week's C3 AI Digital Transformation Institute seminar. C3 AI DTI's mission is to attract the world's leading scientists to work on coordinated and innovatively to put effort in problems that are interdisciplinary, that is related to machine learning, engineering, operations, and computer science. And the goal of this institute is to address problems and make breakthroughs on the ends that have high societal matters. Okay, so I want to give a second to thank the academic as well as the industry partners. And the series of this semester has a theme on incentive design and learning for societal systems. And we have 3 more talks for this semester, including the one at this week. If you have missed the previous talks, we have the recordings available on our website as well as on our YouTube channel. So this week, we're very excited to have Professor Ruta Mehta to talk about her work on allocating goods, bads, and mixed fairness and efficiency through competitiveness. Ruta is an assistant professor of computer science at the University of Illinois at Urbana-Champaign. Prior to joining UIUC, she was a postdoctoral fellow at Simons Institute, UC Berkeley, and at College of Computing, Georgia Tech. She did her PhD from the Indian Institute of Technology, Bombay, India. Her research interests lie in theoretical computer science and its interface with economics, game theory, fair division, and learning. Her honors include NSF Career Award, the Simons Berkeley Research Fellowship, and the Best Postdoctoral Award. Her PhD thesis won the ACM India Doctoral Dissertation Award and the IIT Bombay Excellence in PhD Thesis Award. So let's welcome Ruta. And the talk will be 50 minutes, and please use Q&A to submit your questions. I will ask these questions on your behalf. And thanks, Ruta, the floor is yours. Yeah, you can start sharing your slides. And I will mute myself.
Okay, so you can see the slides?
Yes, it's good.
Okay, thank you everyone for joining. And this is a joint work with Shant, Bhaskar, Jugal, and Peter. And I'm really glad to be here to tell you about this exciting new work. Okay, so we are trying to do this allocation of goods, bads, and mixed to a set of agents. So the setting is this: you have a set of items. It could be goods, meaning things that people value, bads meaning chores, like household duties, teaching duties, stuff like that. And it could be mixed of these, and you want to assign it to a set of heterogeneous agents. And we want to do it, the high level question is to do it in a fair and efficient manner. Now, why do we ask this question? Well, starting from the Bible itself, where there's a question of land division, and cut and choose is a mechanism proposed. Actually, it's a really fun thing to know. Like the fair division, people cared about even like 2,000 years back, of course. And still the question is like equal relevance in the current situation. Like suppose you want to assign landing slots or gates when during inclement weather to different airlines, or school or course seats assignments, or vaccines to different states, or kidney exchange, or dividing assets and liabilities among the stakeholders when you're dissolving a company, let's say, or maybe dividing budgets or duties between different wings of defense. So I mean, this is kind of one motivating slide. I'm happy to, if you have any questions about applications and so on, but now on, I'm going to delve into what the question is and how we going to solve it. Okay, so a little bit about the framework. So we have a set A of agents, n agents, let's say, and m items, divisible, So think of it as time, or let's say milk or bread, stuff like the things that can be divided. And we want to divide these items among agents. How do we know what agents value? Well, we are given valuation functions of agents, and it's difficult to assume that these valuation functions are concave. Basically, concavity in economics is used to capture decreasing marginal returns. So when you value something, I give you more and more of it. Every extra unit gives you lesser and lesser happiness. And for the chores, it's like increasing marginal pains. Okay. These are typical assumptions. Again, just reiterating, the goal is to find fair and efficient allocation. So now fairness and efficiencies are essentially like subjective notions. Something that is fair for you may not be fair for me. So let's first understand, how do we formalize fairness and efficiency through this thought experiment. So suppose we have this half moon cookie, half chocolate, half vanilla, and we have these two agents, Alice and Bob. Bob likes both chocolate and vanilla equally. Alice hates chocolate, she loves vanilla, let's say. Okay. And they don't know about each other's value, and they want to divide this cookie. Or we want to divide this cookie among them. That, let's say, first fairness. Just focus on fairness. And suppose I give you these three possible divisions where the red line is the cut, and A part goes to Alice, B part goes to Bob. Which one do you think is fair? As I said, there is no one particular answer, right? Because something fair for you may not be fair for me. Any thoughts? Okay, you may say that maybe A, maybe 1 is fair because both of them are getting equal amount of both sides. And then nobody can say that I want others allocation. So everybody, both of them will be happy with their own allocation, and they will not say, oh, I should have got the others allocation. But that is also true for, let's say, 2, right? Alice gets more of vanilla than chocolate, and Bob gets more of chocolate than vanilla. Bob doesn't care what amount of vanilla or chocolate he gets. Only if he gets 50% of it, total cookie, he's fine, right? And Alice is getting more of vanilla, what she likes more, right? So maybe this is more fair, but maybe they're equally fair. And maybe third one. So definitely in the sense, if we define fairness as nobody should envy other, that means that nobody should say that I didn't get a fair share, I want the other share. Okay, in that sense of fairness, all three are fair. But the last one is the most efficient one because we are getting kind of a Pareto optimal solution there, where Bob gets half of the cookie and he doesn't care which half he gets. So he gets, let's say, chocolate. And Alice gets everything that she likes, right? She likes chocolate 0% and vanilla 100%, and she gets almost all of vanilla. So in that sense, maybe third outcome is fair as well as efficient. Okay, and let's now formalize this. So many different notions of fairness and efficiency are studied in literature. I'll tell you the most celebrated and the basic notions, the envy-freeness that I hinted in the previous example. So we say that an allocation is envy-free if no agent envies others' allocation. No agent should say that I don't like my allocation, I like that others' allocation. Okay, so let's say in this example, I just want to keep this as a running example. Let's say Alice and Bob items are, let's say, milk, bread, and cheese, and the valuations are additive. So for Alice, if you give her milk and bread, her value will be 3 plus 2, which is 5. Okay, so 3 to 2 are her value for, let's say, milk, bread, and cheese, and they are additive over the bundles. Okay, now not giving anything to both the agents is envy-free because both allocations are the same. They cannot say, I like the other's allocation more. But this is a really bad allocation, right? Because nobody is getting any value out of it. So then proportionality says that every agent gets at least average of her value for the entire bundle. Okay, so if there are n agents, then she gets her total value for the entire bundle if you give her everything, divide by n. So like fair share or equal share, if you wish. Okay, and giving half, equal amount of every item to both the agents, half and half, is proportional. But is this a good allocation? Probably not, because see, Alice likes milk more and Bob likes cheese more. So why is the allocation not kind of skewed like that, right? In other words, this allocation is not Pareto optimal. There is another allocation that both of them prefers over this allocation, right? So if you give all of milk to Alice, half of bread, and then Bob gets half of the bread and all of the cheese. Both of them prefers this allocation to getting half of all three items, right? So definitely this is better than getting like equal share of all the items. And indeed, this is a Pareto optimal allocation in the sense that there is no other allocation where everybody is happier. So we say that an allocation is Pareto optimal if there is no other allocation where everyone is happier. Okay. And finally, we could try and do some welfare maximization. So in particular, suppose we do just usual welfare maximization for this particular example, then Bob's value for all the items are much larger than Alice's value, which is 20, 20, 30, which is much larger than 3, 2, 2. So we should give everything to Bob if you want to maximize welfare, right? But again, that's not fair in some sense, right? It might be that Bob is measuring his value in rupees, Alice is measuring her value in dollars, and that's why they are not saying they are not at the same scale, right? So typically to circumvent that in economics and in this literature, we focus on Nash welfare maximization. This is maximizing the product of the values, not the sum of the values. And what this achieves is scale invariance. So if you scale any particular agent's value by, say, a constant, let's say 10, then the outcome is not going to change because this objective only gets multiplied by 10. So the outcome doesn't change. Okay. So these are the notions of fairness and efficiency we'll aim for. And remarkably, this competitive equilibrium with equal income achieves all four together. Okay, so let me tell you what this is. This is a classical concept, the fundamental concept in economics that comes from understanding markets, essentially. So what's the basic form of, what's the setting here? So now think in terms of markets, economics, okay? So you have a set of agents who are buyers. They have money and they want to buy stuff from this money, whatever they like, okay? So you have goods and they want to buy these goods. Once you post prices, depending on how much money they have and depending on what they like, they're going to demand items, okay? And one thing to note here is that when they demand, they don't know how much is the supply. So it might be that there are only 3 units of the 3 loaves of breads are available in the market, but an agent may demand, let's say 10 loaves because he has enough money to buy so many, okay? And so he's going to demand. The idea is that the market will capture this demand somehow, will get to know about this demand, and it will adjust its supply accordingly. Okay. The other thing to note is that because the agents have fixed budget, some limited budget, they will try to buy those items that give them maximum value per dollar spent. Right? So that's how individually buyers will decide what they want to buy. Once everybody decides what they want to buy, you aggregate demand of all the buyers for every item. Okay. So this, once everybody decides what they want to buy, you get a demand for each of these items, which is totally for, let's say, for how many breads in total is in the demand. At equilibrium, demand should be equal supply. If this aggregate demand meets the supply of every item, then we say that these prices and allocation are at competitive equilibrium or market equilibrium. Okay. And we call it competitive equilibrium with equal income if every agent has equal buying power. That means if we give exactly $1 to every agent, and now we run this market, and whatever the outcome of its prices and allocation, we call that competitive equilibrium with equal income because everybody has equal buying power. And it's not very difficult to see that the corresponding allocation is going to satisfy all the properties that we talked about. So let's start with envy freeness. Do you see why it satisfies envy freeness? So you have $1, I have $1. We face the same set of prices, but you buy what you like the best and I buy what I like the best. Why didn't you buy my bundle, although you could afford it? Because we both are buying a bundle worth of $1, right? So you bought your bundle, not my bundle, because you like your bundle more than my bundle, right? So that's why we get envy freeness for sure, right? Once you have envy freeness, that means everybody likes their own bundle more than anybody else's bundle. And the fact that supply equals demand, that all the items are completely allocated, you get proportionality for free, okay? And again, by fact that supply equals demand, that means total price equals total budget, and everybody buying their best bundles, you get Pareto optimality. And this is also very well-known folklore for welfare theorem in economics, that market equilibrium allocations are always Pareto optimal. Okay, and I'll tell you why it also satisfies Nash welfare a bit later, but okay. And there is a rich history of literature within economics studying competitive equilibrium for goods case. Okay, they don't only focus on this really simple market. They come the market they consider is really general barter system. Like goods and agents are not separate. Agents brings goods that they swap with each other. There are firms, and so much complex setting. And they study existence, properties of equilibria, stability of equilibria, lots and lots of things. So rich history there. Within computer science, it's really like from the very beginning of the AGT field, we started asking questions about computational aspect of competitive equilibria. Can we compute them fast? Okay, and we got some answers already from economists. Like convex, there were convex programming formulations known when valuation functions are special, like one homogeneous. Again, I'll tell you what that means in a bit. And then there were 4 of work finding convex programming and formulations for more general markets. And there are strongly polynomial time algorithms, even when the system is a barter system, but when you're restricted to linear valuations. When you go beyond linear valuations, things become hard computationally, but there are simplex like path following types algorithm that I have worked on a bit. If you go beyond gross substitute valuations, if you know what that means, if you don't know what that means, don't worry about it. Problem becomes computationally hard, intractable. So PPAD hardness, fixed P hardness. So what I'm trying to say is that this problem is still like so much literature and still under study. So really, really important concept, both within AGT and in economics. But what about bads? What about chores? What about market for chores? This is equally relevant, right? But now in the chores market, agents get pain, dissolution by consuming these chores, by doing these chores. So they're never going to buy it, right? They're never going to pay money to buy it, right? So the payment has to reverse. Now you have to post prices which says that if you do this chore, you're going to get paid so much money. And now agents have earning requirements. Okay, so imagine it's a reverse money flow now. Okay, agents have earning requirements instead of spending budget. Okay, and you have prices on the chores, or which says that how much they get paid by doing these chores. Okay, so it's exactly same setting, only the payment is reversed. Okay, and now again, based on their earning requirement, how much pain they incur by doing these chores, they will demand their optimal bundle. When you aggregate the demand of all the agents for a particular item, you get a total demand for that item. And for every item, if you get demand equals supply, then we say that these prices and allocation are at competitive equilibrium. Again, competitive equilibrium with equal income is the same thing, only that now every agent has exactly same earning requirement. Let's say $1. Okay, so everybody has to earn $1. Okay, so that's that. And for mixed, the things are a little bit more complicated, because now the mixed is really mixed. It's not only that you have goods and chores, but you could have that there is an item that is a good for some agents and a chore for some agent. Imagine you are dissolving, let's say, a company, and there might be some asset that liked by some stakeholders and disliked by some stakeholders based on their requirement, their geographic locations, and so on and so forth, right? So you could really have that kind of setting. And now, before you even set prices, you have to demarcate what are really goods and what are chores. How do you do that? So all the items, any item that has at least one agent who values it positively, for whom it's a good, you keep it as a good. All other items are negatively valued by all the agents. Those are real chores. And the goods are going to get positive prices, chores going to get negative prices. Again, everybody demands their optimal bundle based on their budget between negative, positive, and then at competitive equilibrium, demand equals supply. Okay, and now defining competitive equilibrium with equal income is a little more difficult, because what should be budget? Should be +1, should be -1, should be 0. What should it be? It's not clear. So I'll tell you what that is later at the end of the talk. Okay, because mixed is really complicated. Now on, I'm going to mainly focus on chores, which is an understudied question. Okay, so for the chores question, mostly things were open until Bogomolya, Mola, Sadmorsky, and Janowski came up with this really nice result in Econometrica that characterizes the CEI when the valuation functions are one homogeneous. So this one homogeneousness somehow is very central to these markets, and for these markets. Okay, so what is one homogeneous? You have the set of concave utility functions. This is all utility valuation functions. One homogeneous are the ones where if you scale the bundle or the input by a scalar alpha or a, then your value just gets scaled by a. That's one homogeneous. And it captures interesting classes of utility functions. CES is constant elasticity of substitutions, is very central to economics. And subclass of that is linear, which is very central to fair division literature in general. Okay, are there any questions, Maxie? Okay, so they gave a really nice characterization for CEI, but more importantly, they noted that even if all the items are bads, that means chores, negatively valued by every agent, and the valuation functions are just linear, simple linear functions, still the set of competitive equilibrium can be highly non-convex and disconnected. In contrast, for goods, we have convex programming formulation. So not only that the set is convex, there are convex programming formulations whose solution capture those equilibria. Okay, so this was very surprising. And on the computational front, we only know that when number of agents or items is a constant, then we can do it in polynomial time. And these are essentially really smart enumeration methods, like you somehow do observe some properties based on constantness of number of agents or items and do enumeration. But what about complexity in general? Can we compute the CEI even when without these assumptions? And these guys themselves kind of observed that because of this really complex solution set, it might be difficult computationally. Okay, and so we asked, can we even get a, let's say, approximation algorithm? Find approximate polynomial time algorithm to find approximate CEI. And so that's our main result. So what we get is that a new exterior point continuous optimization method that finds an approximate CEI. So initially, I'm going to focus on only bad mana. That means all the items are just chores and agents have linear valuations. And then we could extend it to one homogeneous valuations and also to mixed mana. And mainly in this talk, I'll be kind of focusing on this exterior point method because I find this, it might be that this might be more broadly applicable because it seems generalizable to any non-convex program, convex formulation with separable monotone functions. And for the more general exchange model, things become much more hard. So even existence was not clear when not everyone can do every chore. So, okay, so even if we kind of restrict ourselves to all chores, linear valuation, existence was not clear. So we give a kind of really interesting proof for existence, which uses two fixed point theorems, one nested inside other. So generally, fixed point theorems are very commonly used in economics to prove existence of equilibria in general, Nash equilibria, market equilibria, different types of equilibria. So this is kind of a different kind of proof that I will tell you if we have time at the end. And in terms of computation, surprisingly, we show that the problem is PPAD hard. So just want to draw a contrast with the case of goods. There are strongly polynomial time algorithm available for this case when all the items are positively valued. But if all the items are negatively valued, then the problem is intractable, basically, unless PPAD equals P. And for more general separable concave utility functions, there were no algorithms known, and we give this simplex-like path following algorithm. And there are some interesting consequences of it. So in this talk, as I said, I want to focus on this exterior point method. And then if time permits, I'll tell you a little bit about this existence proof.
Ruta, I have two clarification questions. One is that in all the models and results you mentioned, is there an assumption about whether the good or the chores are divisible?
Yeah, so all of these are for divisible.
So the competitive equilibrium may fail to exist even if it is divisible.
Indivisible, yes.
Okay,
if the items are indivisible, then CI may not exist. Yes.
I see. The second question I have is comparing this one homogeneous value function versus linear value function. Like, how much more general the linear function will become in terms of like the applicability aspect?
So it seems that if you look up the literature in economics, they really like CES. So you can think of CES as P norm function. So what is linear? Linear is less summation of Vij, Xij, right? Vij are the constants. Vij is the value for agent I, value of agent I for item j. If you give Xij amount, then she gets Vij times Xij and sum over that. Okay. Now you generalize it to, let's say, Vij, Xij to the power rho, and the whole summation power 1 over rho.
Okay, I see.
And now the rho is going to range from 1 to minus infinity.
Okay.
So it's kind of a P norm, but with P going from 1 to minus infinity.
I see.
So it's in that sense, it's general mathematically for sure.
Yeah.
And also in economics, it's called 1 over rho is 1 minus 1 over rho is constant elasticity of substitution, and it's important parameter. Yeah.
Yeah,
so
that makes a lot of sense.
Yeah.
Thank you.
Okay, so let me get started with this algorithm. So let me just recall the setting. We have set A of agents. Every agent has exactly a requirement of earning $1. M divisible chores. So chores meaning negative valuation. So for agent I, chore J, let's say, gives Vij value, which is a negative value per unit. So if you give her Xij units of that chore, she gets Vij times Xij pain. And this is her total value. Now, because these are negative numbers, they are difficult to keep track of. So I'm going to think of them as dissolution, which is the mod of Vij's. And now agents want to, instead of maximizing Vi, they want to minimize the Di, to minimize the dissolution or pain, if you wish. And recall, at competitive equilibrium, we are trying to find these prices such that when every agent demands their optimal bundle, that means a bundle that earns her at least $1, right? So if P1 through PM are prices and X1 through XM are allocation for agent, then P dot X vector, this dot product of these two vectors is her earning, right? Because from doing chore J, Xj amount, she earns Pj times Xj. So this is her total earning. That total earning should be at least 1. And subject to that, she minimizes her total disutility. And once everybody does that, we should have that total demand for every chore J, which is summation I Xij, right? Because Xij is amount of chore J assigned to agent I. This summation should be exactly 1 because it is without loss of generality to assume that supply of every supply of every chore is 1 because it's divisible. Okay. Okay, sorry. Yeah, so we are here. Okay. Okay. So let me tell you what the BMSY characterization is, because that's what we use very crucially. So they said that, okay, let's I don't want to worry about the supply equals demand. So let's upfront assume that we are only going to consider those allocations where supply equals demand. So I'm going to call X feasible if for every chore J, the total allocation of that chore is exactly 1 unit, which is the supply. Okay, and it's a feasible allocation. That means you're not assigning anything negative. So X greater than equals 0. Under this feasibility constraint, just minimize this Nash welfare, the product of the dissolution. Now, if you only trying to minimize this product of the dissolution, do you see a very trivial solution to this problem? So what is happening here? Each of these dixi is going to be a non-negative value, so the value greater than or equals 0, right? So the minimum possible product value is going to be 0. So if I can make one of the dixi to be 0, then I don't care what the other di values are. So what I can do is, for one of the agents, I can give just nothing. Set all the xij for that agent to be 0. Okay, so suppose we have at least 2 agents, then I pick agent 1, give nothing to her, give everything to second agent, then d1 will be 0, d2 will be something. But I don't care, d1 times d2 is going to be 0. And that's the minimum possible value. Right? But that's a kind of that allocation doesn't make sense. It's not going to connect to any competitive equilibrium. Okay, so then they impose that we not only want to minimize this, but we also want to make sure that every dissolution is strictly greater than 0. So now this particular program has uncanny resemblance to the classical Eisenberg-Gale convex program for goods case. It just maximizes the Nash welfare, the product of the values. And there, now working with the product is a little bit difficult. So let's apply log. Log is an increasing function, so I'm not going to change the problem itself. But if you do a log of a product, there will be sum of the logs, right? So on both the sides, I'm just applying logs and it doesn't change the problem. But now look at this green part, the goods part. That's a nice thing, right? You are maximizing some of the logs, which is a concave function. It's a convex program. And so here, even if you only ask for local optima of that, the local optima is going to be global optima, and we know now continuous optimization method, even combinatorial method to find it. But here, this is minimizing a concave function. Okay, so it's a non-convex program, but we are only after local optima of this non-convex program. Okay, so we want to find kind of the points that minimizes this product. Now, if you just try to minimize, as I said, there are trivial solutions which are making one of, let's say in this diagram, one of the d1 or d2 to 0, but we want to avoid those local opt. We want to find other local opts. Okay, so this is what BMSY characterization is. Okay, and the main issue here, like when you say find a local opt of a non-convex program, apply gradient descent, right? Obvious thing. Well, the problem is this open constraint, and I'll tell you in a minute why. Okay, so far this is the situation that we have seen, right? So now what we are after is local optima of this program. What do we mean by local optima mathematically? So this is geometric view here. Okay, so you take a gradient of this objective, which is for ith coordinate, the derivative of log di is 1 over di. So ith coordinate is 1 over di. And at local, d star is a local optima. Then when you look at the supporting hyperplane at this point and look at the normal should be proportional to the gradient. Then only it can be local optima, because if you try to go in any nice direction, which is kind of making less than 90-degree angle with minus of 1 over di, which is the direction of movement, if you want to improve this objective, reduce this objective, then you're going to go out of the feasible region, and that's why it's a local optima. So basically, it's a KKT point condition, right? So normal to the supporting hyperplane should be proportional to the gradient. Okay. Why does it give CEI? So let me give you a brief proof sketch. So here is the characterization of CEI. So optimal bundle. In optimal bundle, note that if this is the dissolution you are trying to minimize subject to earning constraint, you should only demand those items or those chores that give you minimum pain per dollar earned. Because you don't care how much supply is available. You just demand whatever give you minimum pain per dollar earned, minimum density per dollar earned, right? So you will only demand those items that give you minimum pain per dollar earned. And in that case, your total pain is going to be dollars earned times pain per dollar earned. But this pain per dollar earned is going to be the minimum one. So this is going to be this minimum pain per dollar earned times 1. So the point I'm trying to make is that the distributivity obtained by every agent is going to be exactly this MPBI, minimum pain per buck. Okay. And on top of that, we're going to have demand equals supply. Okay. So look at this. Now, in this program, there are no price variable, only allocation variable. So how do you get prices? So suppose we have this point here, which is a local op. Let me define the price J to be, so I have this gradient and the normal AI, right? Set Pj to be min of over all agent I, AI times Dij. This is somehow magically, I tell you, this is the price you set. Now look at the allocation at this point at these prices. I'm going to claim that it is an optimal bundle at these prices for every agent. Why? Well, just from the definition of these prices, we know that for every agent I and chore j, we know that Pj is less than equals AI times Dij. If you do some manipulation cross product, then you get 1 over AI less than equals Dij by Pj, just manipulation. So because this is true for every I and j, we know that for every agent I, 1 over AI should be at most min of these Dij over Pj values. And so it must be at most MPBI. Now, using the fact that there is a supporting point here, we can prove, so I'm skipping some steps here, but just believe me, using this fact that D star is a feasible point, we can prove that 1 over AI is exactly MPBI. And now we are done. Why? Because at this point, we know that 1 over AI is going to be Di star, because we have that normal is proportional to the gradient, right? So we have that Di star is 1 over AI, which is MPBI, and this is exactly the condition we need to get optimal bundle, right? This is what we proved in the previous slide here. At optimal bundle, the distributivity should be exactly the MPBI at the corresponding prices. So at these prices, the corresponding allocation at D star must be at CEI. This is what they basically proved. This is BMSY proof actually. Okay. And now note that if you, instead of exact KKT condition, if you have approximate KKT condition, that is normal is approximately proportional to the gradient, then we get, in the previous slide, Di star is 1 plus or minus epsilon over AI, which is 1 plus or minus epsilon 1 MPBI, which is exactly just MPBI times spending 1 plus or minus epsilon, or earning 1 plus or minus epsilon. So you still, every agent is consuming at the minimum pain per buck chores, but they are not earning exactly 1, but 1 plus or minus epsilon. Okay, so this is our definition of approximate CEI. So if we get a point which is epsilon approximate KKT, from that we can extract an approximate CEI. That's the point. Okay. So now, okay, so now the problem is now just to find an approximate KKT point of our problem, which was of this program. Okay, and by D feasible here, I mean that there exists a feasible allocation that achieves that distributivity value. Okay. So then why not just apply gradient descent? The problem is, as I said, these open constraints. Yeah, Maxi, question?
Yeah, I have a question. So in the formulation part, is there any part that restricts it to only apply for chores instead of goods?
So in the goods case, you want to maximize
the
objective. Yeah. And that's just convex program, because you are maximizing a concave function.
Okay. Okay.
And that's a convex program that we know how to do.
Okay, I see.
The problem was with minimization. We don't know actually. So just if you don't have these open constraints, d greater than 0, then it's easy. But the open constraints are the problem.
Okay. Thank you.
Yeah. So the problem is to kind of these why these are the tricky constraints? So look at this objective and its gradient. So if you want to minimize some of the logs of di, you will try to move, the gradient descent will try to move in the direction of -1 over di, because 1 over di is the derivative of log di, and then minimization, so you move in the -1 over di direction. But then it will look at the smallest, so you have a d vector, let's say, a feasible d vector. Look at the smallest di coordinate. 1 over di will be the largest for it, and it will decrease that particular coordinate fastest, right? So what it is trying to do is that it is decreasing the smallest coordinate faster. So it's trying to make that particular coordinate to get to 0. Okay, and even under experiments, we saw that this is what is happening. Okay, even if you add barrier functions, you do add extra constraints, it will go to those extra constraints, and those are not corresponding to equilibrium. Okay, so no matter how you try to tweak it, gradient descent will always try to take you to these points that are basically not allowed because of the open constraint di greater than 0. Okay, and basically what is happening is that these local optima that are we desiring are not quite stable. So if you go a little away from it, the gradient descent will take you away, really away from those desired solutions. So then we said, okay, so there is no hope of kind of doing something from the interior using gradient descent. So we said, let's look at the let's flip the problem. Let's look at the problem from the outside, from the exterior region. And in this diagram, the exterior region is this blue region. We have to define it properly, but it is basically the region in the positive orthron that is below this polytope. Now, what do you mean by below this polytope? Well, we can define it for this particular polytope because it has a nice lower hull, but in general, it's not quite clear. Okay, so, but if we can define this exterior region properly, then you, instead of minimizing now in the exterior region, you would like to maximize. Okay, so the local max from the exterior region will be actually local min from the interior. And this is because basically the local max from the exterior will still have to satisfy that KKT condition that the normal to the supporting hyperplane is proportional to the gradient. And that's the condition we also require from the interior local min. And so basically they match. Okay, and now this is good because when you try to maximize this product objective or some log objective, you will move in the direction of 1 over di, which will increase the smallest coordinate fastest, and it will never take you to the 0. Okay, and so this is basically kind of high-level intuition for applying exterior point method. The problem is that first of all, the exterior region is not well defined in the allocation space. It is only well defined in the disutility space. So first we have to map allocation space to disutility space. Then second thing, this is going to be definitely non-convex region. Okay, so we're not going to be able to apply some known method directly. Third, the potential function. What should be potential function? It's not clear. And then how to show fast convergence, that's also not clear. So let's first focus on the potential function and just see whether this objective that we are trying to maximize from the exterior indeed can act as a potential function. And so let's take any exterior point E. Suppose we project it on this polytope. We prove that this projection is going to be coordinate-wise more than E. Why? Because we have this fact that from E, if you move in any positive direction, you're going to hit the lower hull of this polytope. So using this fact, we can prove that when you project it on this polytope, the resulting point is going to be coordinate-wise more. And then clearly this objective will improve. Now what do? Now you went from exterior to a feasible point. And still we don't know how much progress we have made. So then we say that, okay, look at the supporting hyperplane. Okay, if we are not already at an approximate KKT point, that means normal is not proportional to the gradient, then maximize the sum log objective, this objective that we are after. And then you will hit another point because of this sum log objective, the way it is, we know for sure that it will never go out of the positive orthorent, and it will always remain in this exterior region. That's why. Okay, so because this when we are doing this maximization of sum log objective on this hyperplane H, we completely forget about this feasible region for the disutilities. Okay, so this hyperplane might be going in all the orthorents, all the negative positive orthorents. Okay, but because of this objective, the way it is, it will never make any of the coordinate negative or 0, and we know therefore that it will always be in this exterior blue region. And then because we strictly maximize this sum log objective, we must have improved from when we go from this D to E prime. And this gives us a potential function, and basically we stop when normal to the supporting hyperplane is proportional to the gradient, right? So this essentially gives us the algorithm. So you start with exterior point, project to the feasible region, look at the supporting hyperplane. If normal is not proportional to the gradient, approximately proportional, then you maximize the objective, you go to another exterior point for sure. There you definitely improve the objective by a lot, and then you repeat until we find an approximate KKD point. Now, we already kind of discussed why approximate KKD gives approximate CEI and why this objective is a potential function for this particular method. But the question is, why should this method ever stop, right? It could be that every improvement is very, very tiny and you are not making large improvement to really argue about finite convergence, let alone polynomial time convergence, right? And so we show that this lemma was very crucial, that the increase in potential is at least lower bounded by something if you are not already at an approximate KKD point. Okay, and here the intuition is just that if you are not an approximate KKD point, then it must be that the budgets are more imbalanced than 1 plus minus epsilon. And then when you go to E prime, the budget is going to get balanced. And balancing budgets is same as balancing the disutility. And this objective improves. The product objective always improves as the coordinates in that product objective balances out. Okay, and so this improves this. And when you put all these three lemmas together, we get the final theorem that the search has to terminate in polynomial time because this total objective value is upper bounded by the bit length of the input. So this is kind of overall proof. When we try to extend it to one homogeneous case, all these nice things about linear utility functions working explicitly with this utility space and so on goes out, because now function, you don't know what the form of the function is, just Oracle access. And the corresponding D space, this utility space, is not convex anymore. So we have to extend it. When you try to find the nearest feasible point, we'll have to use some kind of a gradient descent or convex optimization method, which will only give us an approximate solution. So when you do the projection, you're going to get approximate projection and then approximate supporting hyperplane, not even a proper supporting hyperplane. And everything adds error. The point is that while working with even with pre-images and so on, I mean, with linear, it's easy. It's not as easy with the value oracle model. All of these errors do not add up and gives us garbage. I mean, finally, we'll get something reasonable even after handling all of these errors. That was the kind of, this is actually the most technical part of the proof, actually. And finally, I just want to note that we can extend this to unequal income type of thing, where every agent had different earning requirement. In fair division, this matters when not every agent is equally important. Maybe different agents have different importance, and then accordingly, you may want to do the division. Like say some airlines are huge, so maybe they should definitely get more landing slots than some smaller airlines, something like that. Okay. And also to mixed mana. Now, as I hinted, for mixed mana, it's not very clear how to define CEI. So first, BMSY says that given any instance, you can classify it as positive, null, or negative instance. I'm not going to give you classification, but once you do these classification, positive instance essentially works like a goods mana. Null instance is like just you give every agent an allocation that gives them 0 utility. And for negative instance is essentially like a Boltzmann. And so positive instance can be solved by this Eisenberg-Gale convex program, negative instance by our method. And so we extend our method. We have to do a little more work because now the feasible and exterior region are not so nice, but finally everything works out. Okay, so I think I'm about time, right, Maxine?
Yeah, so if you want to briefly mention the second part, I think we still have a bit of time, but I try to limit it maybe to 7 to 8 minutes.
Okay, sounds good.
Thank you.
Yeah, okay. So for the barter system, which is much more general model, let me just tell you what the model is. Same setting, but now agents don't have any particular earning requirement. They bring some chores to get done. Okay, and to get these chores done, they'll have to pay. So that defines their earning requirement. Okay, so let's say Wij is the amount of chore j that agent I brings. So they have this much of chore to get done. And when all of these Wijs are 1, this is exactly CEI. So CEI is a very, very special case of exchange model. And surprisingly, we found really like the systems which are doing exchanges. So I don't know if you have heard of Time Bank or came across it. So search timebank.org on Google. It's a system, community service system, where people get together and they are doing each other's chore. So whenever somebody does somebody else's chore, they earn time credit, and they can use this time credit to get their own chores done. Okay, that's called Time Bank. There is also this living for help system in Germany, where old and young people, even though not related, they would live with each other to do each other's chores. And similarly to students teaching each other. And in all of these settings, we observe that not everybody can do every chore. So there'll be always every agent specifies what all chores they can do and what all chores they cannot do. Okay, so to capture this, we allow that some Dij value, the distributive value, could be infinity meaning that agent I can't do chore j. Okay, and once you allow this, the equilibrium may not exist. Now, this is not surprising because this also happens with the goods case, right? So if there is a set of agents who brings some set of chores, but they can only do the subset of it, then there is no way they can earn enough money to get all of their chores done, right? So this is a typical also kind of phenomena that occurs with the goods case, and the equilibrium doesn't exist. And the typical assumption is the strong connectivity of the economic graph, meaning that if you draw this graph between agents where agent edge from I to j, I to k means agent I can do k's chore, then this should be strongly connected. That means you can do flow of chores from anybody to anybody. So under this assumption, for goods case, equilibrium exists. For chores case, still doesn't exist. And it is NP hard to check whether it exists even for constant approximation. So this was very surprising. And then we impose this assumption too, which is saying that every pair of agent has either same set of skills or different set of skills, meaning they can do either same set of chores or different set of chores. Okay, and under these two assumptions, we show that this second assumption is kind of unavoidable, right? Even if there is one disparity, then equilibrium may not exist. And under these two assumptions, we show that equilibrium always exists. The difficulty here, let me not go into the difficulty, but I just want to mention, as I said before, that the proof is a little different than the classical proofs for existence, in the sense that we use both Brouwer and Kakutani, one nested inside another. And somehow this was kind of unavoidable in some sense because of this issue of undefined optimal bundle at 0 prices. So imagine you have some set of chores that has positive prices, but the set of chores that you can do has 0 price. Then there is no way you can earn enough money, because you can't earn anything to get your chores done. So optimal bundle set becomes like undefined here. And yeah, so we kind of circumvent this by doing this, and that was an interesting part. What about computation? We thought that initially it should be polynomial time, tried, never succeeded. And then eventually we showed that it's PPAD complete. Very disappointing, actually. But this gives us a nice dichotomy between exchange and CEI, that for CEI, we can do 1/Polyn approximation in polynomial time, but for exchange, it's PPAD hard. And this is very typical to chores, even with, this is with linear, where in linear goods, both are strongly polynomial time solvable. Then we designed recently some combinatorial algorithms, because combinatorial algorithms tells you more about, so when you run this exterior point method, we don't know what's happening with the market. But typically what you want is that even with the goods, initially we came up with this more general continuous optimization like algorithms, but then we started coming up with this combinatorial algorithm that tells us what's actually happening in the market. And that's very useful actually for other aspects, to understand other aspects as well, like dynamics and so on. Okay, so we came up with this interesting combinatorial algorithm that kind of beats our FPTAS and gives exact CEI for special cases of utility functions of this type, 1 plus alpha to the Kij, and also puts the problem in CLS. But these are the difficult, hard questions. What is the exact complexity of CEI? Is it CLS hard, or is it polynomial time? Any other aspect of this problem, strategic analysis, dynamics, like proportional response type dynamics on this market, would it converge? If converges, would it converge to competitive equilibrium? Learning aspects, lots of work on learning aspects for goods case. Work for chores, I haven't seen. Okay, so maybe there might be something at Simon's in this workshop that's happening, but I don't know. It would be very interesting to see. And for the goods case, the competitive equilibrium for the divisible has been crucially used for understanding many aspects of indivisible goods. Can we do the same thing with indivisible chores? Okay, like I don't know, if you know about EF1 and PO, then you would appreciate this question, that these are for the indivisible items, the NV freeness and proportionality, these things don't exist. So you have relaxed notion of NV freeness, which is called EF1 and EFX. And really simple question like whether there exists an allocation that is, let's say, NV free up to one item and Pareto optimal, we don't know. Okay. So all of these interesting questions it would be interesting to know if any of these CEI technique can be applicable here, or in general can be solved. So basically, I'm trying to say through these open questions that basically for the chores, forget about mix, for chores even, most of the questions are open. And yeah, I would like to stop here, and I thank every one of you and also my collaborators. Thank you.
Yeah, thanks, Ruta. We're open to questions both from the audience and the panelists. If you have questions, please submit through Q&A, or if you're a panelist, just unmute yourself and ask. Meanwhile, I have a question about the first part of the talk. So, so when you have this minimization over functions that does not have convexity or concavity properties, this is the challenge like arises because you don't really have a well-defined dual problem for this thing. But I saw that your algorithm still takes a lot of inspiration from this gradient descent, gradient related. So I wonder like if there is still some connection with respect to like dual, or if this question makes sense or not.
Yeah. So actually, when we say KKT condition, right? So we are essentially trying to take a dual of it.
Okay.
And so okay, it doesn't have a proper dual, but you can still write a KKT condition. Like you can say that look at the Lagrange multiplier of every constraint and write the dual.
I see.
And the dual variable will be the prices actually. Okay. And because we are not after global optima, we are only after local optima, just the KKT conditions will suffice to prove that they give us CEI. Okay. And because of this, we were hopeful that somehow some kind of gradient descent would work from inside, from the interior. But because the main issue was the open constraint.
Yeah.
The open constraint, right? Somehow, whatever tweak we tried to do with gradient descent, it always led us to hit this open constraint. And yeah, it would be really nice to know if we can still do from the interior using the gradient, or maybe even second order. Let's say second order
sounds to be relevant here.
Yeah. Our experiments, like naive experiments, let's say adding barrier functions and stuff like that, didn't work. But maybe more smarter things, I don't know. And it might be useful also to answer the question I posed at the end, that can we get exact, not approximate CI in polynomial time, but exact in polynomial time. So even if you can, let's say, get epsilon to be, let's say, inverse exponentially small. So suppose you get an algorithm that depends not on 1 over epsilon, but let's say log 1 over epsilon polynomially, then you're done. Okay, so what I'm trying to say is that in this running time, so instead of this order n cube over log L over epsilon square, get log 1 over epsilon. Then I can get your exact. Yeah.
Thanks for sharing your insights. We're just about right on time, and thanks everyone for attending this talk. And I want to thank the speaker again for sharing her work and sharing her insights. Thank you.
Thank you, everyone.